Hello, everyone. I'm Mingshan from University of Technology, Sydney. Today, I will present our paper called Analyzing Egocentric Networks via Local Structure and Centrality Measures, a study on chronic pain patients. I will first talk about the importance of studying egocentric networks and discuss the suitability of several local structure measures and centrality measures. And then I will present our dataset and discuss the correlations among these measures. And finally, I will talk about using these measures to predict the pain grade of chronic pain patients. There are three main differences between egocentric social network and sociocentric social networks. First, they have different purposes. Egocentric social networks is concerned about individual level properties such as a person's health status, his or her propensity, identity, etc. And sociocentric social network, on the other hand, focuses on network level activities such as information diffusion, disease transmission, resource distribution, etc. Secondly, different in range. Egocentric social network focalize on the immediate neighborhood around an individual rather than the entirety of a group. So due to the smaller range, studying egocentric social network is very efficient in computation. And thirdly, egocentric social network is easy and more flexible to collect data, for example, through questionnaires, surveys, or some easy tools. There are many different approaches in studying general networks. Among them, the family of local structure measures is simple in definition and very useful in various tasks. These measures are proposed from the perspective of subgraph formation, defined by the ratio of two numbers of two subgraphs. One contains less edge and is viewed as the formation base of another. Their computation only involves nearby neighborhood of a node and is therefore very fast. Among them, the clustering coefficient is most representative and widely applied in both sociocentric and egocentric networks. Some other interesting measures are recently proposed, including the closure coefficient, the I-quarter coefficient, and the third-order clustering coefficient. These measures have not yet been discussed and studied in egocentric social networks. Let us begin with classic clustering coefficient. It captures the degree to which the neighbors of a focal node connect to each other. From a structural perspective, it measures the formation of triangles upon open triads. Its definition is given in equation 1. The numerator is the number of triangles containing node I, and the denominator is the number of open triads containing node I. Since the definition is based on the immediate neighborhood of a given node, the clustering coefficient is naturally suitable in egocentric networks. As a variation of the clustering coefficient, the closure coefficient is recently proposed by having the focal node as the end node instead of the central node in an open triad. It provides new perspective on network clustering. Specifically, the closure coefficient captures the degree to which the two hop neighbors connected to the focal node itself. Its definition is given in equation 2. The numerator is twice the number of triangles containing node I, and the denominator is the number of open triads with I as the end node. Ti is multiplied by 2 because a triangle can be formed from two different open triads when I is the end node. However, because ego node is connected to every other node, the closure coefficient of an ego node can only be 1 or undefined. Next, let's look at the local structure measures that involves 4 nodes. The I-quarter coefficient is recently proposed to measure the formation of triangles. It is quantified as the fraction of 3 paths that actually from quadrangles or four cycles. The numerator is twice the number of 4 cycles, and the denominator is the number of 3 paths with I as the inner node. When it comes to egocentric networks, because ego node is connected to every other node, the numerator naturally becomes twice the number of 4 caudal cycles, and the denominator turns into the number of tailed triangles. Another interesting metric is the higher order clustering coefficient. When 4 nodes are involved, it is called a third order clustering coefficient. This metric measures the formation of 4 cliques from tailed triangles. Similarly, the denominator is 3 times the number of 4 cliques, and the denominator is the number of tailed triangles with I at the center. Same as the clustering coefficient, the third order clustering coefficient is naturally suitable for ego nodes. Other popular approaches, of course, the big family of centrality measures, and here we cover 4 of them: the degree centrality, the closeness centrality, the betweenness centrality, and the eigenvector centrality. The degree centrality is defined as a number of nodes directly connected to a node. And since in an egocentric network, every node is connected to the ego, the degree centrality of the ego node also equals to the size of the network -1. The closeness centrality measures the significance of a node through its distance to every other node in the network. However, in an egocentric network, the closeness centrality of an ego node always equals 1. Therefore, it is not a discriminative metric for ego nodes. The betweenness centrality measures the extent to which a node lies on the shortest path between other nodes. And finally, the eigenvector centrality measure believes that the importance of a node is determined not only by the number of its neighbors, but also by the importance of these neighbors. Every node is initialized with an importance score, and iteratively, each node updates this score through aggregating the scores with neighbors. From their definition, we know that both the betweenness centrality and eigenvector centrality are readily suitable in egocentric networks. Our experiment is conducted on the real data set collected from chronic pain patients of a Flemish Pain League, the League for Rheumatoid Arthritis, and the League for Fibromyalgia. Each patient uses graphical toolGANSI to generate their egocentric social networks containing up to 10 contacts, including the connections among authors. Participants were also asked to fill out a questionnaire including their socio-demographic and pain characteristics. Among these characteristics, we are particularly interested in pain grade. Patients' pain grade are calculated by means of the graded chronic pain scale, or GCPS, which assesses both the pain intensity and pain disability. And here we have 4 grades level. Grade 1 is of low intensity and low disability. Grade 2 is of high intensity and low disability. Grade 3 is of a moderate disability regardless of the pain intensity. And grade 4 is of a high disability regardless of pain intensity. In the data set, we have in total 303 egocentric social networks. And among them, 248 are females, 55 are males, and their average age is 53.5 years old. Also, the distribution with the pain grade is not balanced. We have 21 patients of pain grade 1, 33 of pain grade 2, 67 of grade 3, and 182 of grade 4. Finally, from the degree distribution, we can see that most most participants have a degree of 10, which is also the maximum degree they can have in this data set. We then calculate the Pearson correlation score among the 4 local structure measures and the 3 centrality measures. We observe strong relationships. Strong means the Pearson score is greater than 0.8 at 5 combinations here. And in order to further investigate them, we draw the scatter plots of the 4 pairs. Pair 1, the I-caudal coefficient and the third order clustering coefficient. As discussed before, the I-caudal coefficient of ego nodes measures the formation of caudal cycles upon tilt triangles, whereas the third order clustering coefficient measures the formation of 4 cliques also upon tilt triangles. From this similarity, we naturally expected a strong positive relationship between them. And also we can see that the third order clustering coefficient is strictly less than or equal to the I-caudal coefficient. This is because one more edge is needed to form a clique than to form a 4 caudal cycle. Pair B, the clustering coefficient has between centrality. Apart from the strong negative linear correlation, we observe that all dots are on or below the line passing 1, 0, and 0, 1. We then propose and prove the following proposition. The normalized between centrality of an ego node is equal to or less than 1 minus the clustering coefficient of that node. The detailed proof can be found in our paper. Pair C and D are similar. Take C, for example, the I-caudal coefficient and the eigenvector centrality. We can see the eigenvector centrality tends to decline when the I-caudal coefficient becomes larger. Moreover, we also find that in the heat map, that 4 local structure measures are negatively correlated to between centrality and eigenvector centrality. This is because when more links appear between alters, the relative centrality of alters rise, which leads to the decrease of the ego node's centrality. We then apply these measures to study the grade of pain. This parallel coordinates shows the average local structure measures and the centrality measures of 4 GCPS grade. It shows that patients with higher order pains, grade 3 and 4, of color red and orange, they are notably separated from patients of lower pain grade, grade 1 and 2, in terms of clustering coefficient, I-caudal coefficient, higher order clustering coefficient between centrality and eigenvector centrality. However, neither the closure coefficient nor the degree centrality is a distinguishable feature because the closure coefficient can only take value 1 or 0, and most of the degree centrality equals 10 in this data set. As discussed earlier, higher values of local structure measures and the lower values at betweenness and the eigenvector centralities indicate better connections in the patient's ego networks. This finding is also in accordance with previous studies that shows social interactions play an important part in the perception of pain. And from calculating the Euclidean distance between each patient's topological feature vector and the group average, we present 2 actual examples from the dataset as the social network prototypes of pain grade 1 and pain grade 4. We can see that social network of grade 4 patient is much less well connected than that of grade 1 patient. Finally, we apply the local structure measures and the centrality measures as additional features in a machine learning task that predicts a patient's pain grade. We feed 4 sets of features into random forest classifier. First set, also the baseline, includes patients' demographic attributes, pain-related descriptions, and physical, psychological well-being indicators. This set is also referred to as raw feature. Second set includes the raw features plus the local structure matters. Third set includes raw features plus 3 centrality matters. And fourth set adds both local structure matters and the centrality matters to the raw features. First, we observe that adding local structure matters or centrality matters as extra attributes leads to marked improvements, especially significant when centrality matters are included. And second, although local structure, we have seen that local structure matters are negatively correlated with centrality matters to some extent, adding both of them still leads to further improvements. The experiment shows that the topological information captured by local structure and centrality matters are beneficial in predicting the patient's pain grade and is potentially useful in analyzing egocentric network in general. And I will pass the conclusion here. Thanks for listening.